Thermodynamics. Now let's begin with something which is very common in your daily life. Suppose you have a cup of coffee and a glass of ice water, and you have to tell which among the two will have more heat. You have to tell whether the cup of coffee will have more heat or whether the glass of water will have more heat. So simply write your answer right now in your notebook, and we will see the answer in the upcoming lecture today, that which of the two will have more heat, and we'll see whether your answer is right and wrong, and if it is wrong, then what is the misinterpretation you made about heat and temperature. So thermodynamics is all about heat and temperature, and today we are starting this beautiful topic, thermodynamics, which will deal with the study of heat, temperature, and the interconversion of heat into other forms of energy. So we'll explore this answer in the coming lecture today. We'll also see the wider interpretation of the term temperature, heat, internal energy, etc. So you can write the heading thermodynamics. That is the main unit which we are starting today. And thermodynamics is a branch of physics which deals with the study of interconversion of heat and other forms of energy. We all know heat is a form of energy, and energy can be converted into another form. So thermodynamics basically deals with the interconversion of heat into other forms of energy and vice versa. How heat can be converted in other forms and how other forms of energy can be converted into heat. All these studies constitute the branch of thermodynamics. Now let's explore the roadmap, how we will proceed ahead in the unit of thermodynamics. So we'll have an idea that how we are going with the topics. Firstly, we will see what is the meaning of heat and temperature, how they are defined, what are their physical significance. Then you will see different temperature scales like Celsius, Fahrenheit, Kelvin, etc., and their conversion with each other. Then we will see the specific heat, latent heat, and heat capacity and the related numerical problems based on these parameters. After that, we will explore the topic of thermal expansion, and then we will see how the heat is transferred. There are three modes: the conduction, the convection, and the radiation. And then we will see Newton's law of cooling and Kirchhoff's law. So this will be the roadmap, how we are going to proceed with the unit of thermodynamics. Now let's see the strategy for getting the optimum output, for extracting the maximum performance out of these lectures or this course. What will be the flow chart? What will be the sequence of steps you need to follow? First of all, you will watch the lecture, make the notes. After making the notes, if you have any doubts or discussion, you can enter in the discussion panel on our portal. There will be a discussion panel, doubt panel, or you can get in touch with me for the doubts. After these two steps, you will work out the related assignment of the lecture. Each lecture will have a related assignment booklet that will be on lecture based. Either you can call it an assignment booklet or DPP, which you will work out. And after these three steps, you will attempt the lecture test, which will confirm that you have an optimum level of learning. And given below in the description box, you will find a link to join us or to land at our portal for the complete course, for the complete material, for the complete test, not only in thermodynamics, but all other branches of the subject too. So you can get with the link below. There are many free material available too in the link. So you can get connected with us by the link given below in the description. Now see, in today's lecture, that is lecture 1, and the code will be TPA01. The code will be like TPA01, TPA02 for this series. So this is the first lecture with the code of TPA01. In this lecture, our learning objectives will be the meaning of heat and temperature, what is the meaning of adiabatic and diathermic wall, what is the meaning of thermal equilibrium. We'll explore the Zeroth law of thermodynamics, and then we'll see how the temperature is defined, the definition of temperature by the Zeroth law of thermodynamics, and then we'll see the conversion of temperature from one scale to another scale, and then the meaning of mechanical equivalent of heat. Now let's see what is the meaning of system, surrounding, and boundary. See, in thermodynamics, when you study something, some part, some object, then that particular part under study is called the system. Suppose we have a cup of coffee, okay? We have a cup of coffee, and you want to know what are the energy changes taking place in the coffee. So you are just concerned with the coffee and nothing else. Okay, you are just concerned with the coffee and nothing else. So this coffee is constituting the system. So what is the system? The part of the universe which is under observation for transfer of heat and other forms of energy. That is the system. The cup is not the system. The material of the cup is out of the system. Only coffee is the system, okay? And everything except the coffee, rest of the universe except the coffee is the surrounding. So what is the surrounding? The remaining part of the universe other than the system is the surrounding. So you can say this room, this cup, okay, whatever is outside the coffee, this is what? This is the surrounding, okay? And the wall, the surface which is separating the system from the surrounding is called the boundary or wall. So what is the boundary or wall? The surface separating the system and the surroundings. Okay, so in thermodynamics, sometimes we will focus on a sample of gas. So that sample of gas will be the system. The container of the gas and the rest of the room will be the surrounding. Okay, if you are focusing on, you say, some sample of water in a glass for the heat transfer, so that sample of water will be the system. The glass will be the surrounding. You can also take the glass plus water as the system. If you're taking the glass plus water as the system, you can take, it is not a rule that only one component can be taken as a system. So you can take both as the system. So now in system, you have glass as well as the water. So any changes which is taking place now between glass and water will be within the system, because you're taking both as the system, glass as well as the water. And anything which is outside the glass or the water will be the surrounding, okay? So we will do problems, then it will become more clear how we choose the system and the surrounding and the wall or boundary. Now, when we talk about the wall or the boundary, it can be of two types, adiabatic or diathermic. Now, adiabatic is something which does not allow any transfer of heat or matter. So if you have two systems and we have an adiabatic wall between the system, so no heat will transfer between them, as well as no matter, that is no mass, can transfer between them. So this is an adiabatic wall. Okay, a wall which does not allow any transfer of heat or matter. Then we have diathermic or diabatic wall. So if you have a diathermic wall, so what is the relaxation in diathermic wall? The heat can flow. Heat can flow, okay? But matter still can't flow. No matter can be transferred through diathermic wall. So the only relaxation which we will have in a diathermic wall, that heat will be allowed to flow through the diathermic wall, while in adiabatic, neither the heat nor the matter will be allowed to flow. So whenever you have an adiabatic wall or container, it's complete insulation. No transfer of heat can take place between the system and the surrounding if there the boundary is adiabatic, okay? Now when we talk about heat, so heat is a form of energy transferred between two or more systems or a system and the surroundings by virtue of the temperature difference. Now there is one very important thing. Heat is a form of energy which is transferred. So it is basically the energy in transit. Whenever there is a temperature difference between two systems, the heat is transferred between one system and the other. So heat is the energy of transit. It is not something which is contained in the object. Very critical point. It is not something which is contained in the object. We can never say something like this: the object contains 50 joule of heat. This is completely wrong statement. Okay, heat is not something that is contained in the object. Got it? Heat can only be talked in terms of transfer. You can say object A is transferring 20 joule of heat to object B. So heat is always something which is property of the motion of the transfer. You can never say object A has 20 joule of heat. No, never. Of course, you can add heat to the body, but it will not reside in the body. You can say, I'm adding 20 joule of heat to object A. But then you think, if I'm adding 20 joule of heat to object A, then where the heat goes? If we say that object A cannot contain heat, and I've added 20 joule of heat to object A, so where this 20 joule of heat has gone? So we'll see later, when you are adding 20 joule of heat in object A, it will get transformed in some other form of energy like internal energy or so. That is the topic of the later part of the chapter. But object A will not have 20 joule of heat, even if you are adding it. It will get transformed in some other form of energy. Got it? So heat is something which is always talked among the topic of transition, motion. We never say object has some heat. Okay? It will get converted to some other form of energy to be stored in the body. Clear? So write it down. Heat is a form of energy transferred between two or more systems or a system and the surrounding by virtue of the temperature difference. And this point is very important. This point is very important. Heat is not something that is contained in the body. It is always a property of transition. Got it? So if I'm going back to the beginning of lecture, where we started with a thing to ponder whether a cup of coffee or a glass of water will contain more heat. Now I think you are in a state to answer. The answer is none. The answer will be none of two. Because I'm talking which will contain more heat. Which will contain more heat. And heat is something not to be contained. It is the property of transition, motion. So when we say whether the cup of coffee will contain more heat or a glass of water will contain more heat, the answer will be none of them. See, from a common man perspective, if you talk about a common man's approach, he will most probably answer a cup of coffee because he will think there is more hotness in the cup of coffee. But heat is not related to hotness. Temperature is related to hotness. So you can say the coffee has more temperature. The glass of water has less temperature as compared to the cup of coffee. But it is not related with heat. When we say something has more temperature, you will see later what it means. It will have more internal energy. It will have more. There will be a form of energy which you will study later. Internal energy. Okay. So when the object has more temperature, it will have more internal energy. Got it? So usually in common language, what we do, we interpret the content of internal energy as heat, which is not correct concept. So here you can say the coffee has more internal energy. The glass of water has less internal energy. Okay, because coffee has more temperature as compared to glass of water. But as far as if you want to say which will contain more heat, the answer will be none. Because heat is not the residual property of the object. It is not something to be contained in the object. Okay. Now this internal energy can be transferred to the surrounding in the form of heat. That is another thing. If the body has more internal energy, if suppose you have some object which has some internal energy, so this internal energy can be transferred to surrounding in the form of heat, because energy can be converted into heat. So heat can only be transferred. Heat can only be transferred. So what will be the proper answer for this problem? You will say number one, neither the cup of coffee nor the glass of water will have more heat, because heat is not the residual property of the object. It is something which we talk about when the energy is in transition, when the energy is in motion. Number one. So as far as the word contain is concerned, nobody will contain more heat. Number two, even if you want to interpret more, then why the coffee is appearing hotter than the glass of water? It is because of its higher temperature. And that's why it has more internal energy. That's why it has more internal energy. And this internal energy can be transferred to the surrounding in the form of heat. This internal energy can be transferred to the surrounding in the form of heat. That's more elaboration, which you're going to study later in the chapter. Our question was limited that which will contain more heat. So as far as this, the crux of the question is concerned, the answer will be none. Now let's see how we interpret temperature. So on a lighter note, if you go for a lower class definition or interpretation, you say temperature is the measure of hotness of a body. But that's a very casual definition. That's why we have written on a lighter note. Now in today's lecture, we will explore more and deeper into the meaning of temperature in terms of the direction of flow of heat, how the temperature is defined by the direction of flow of heat, and then by Zeroth law of thermodynamics. In fact, this Zeroth law of thermodynamics gives temperature its definition. This is the law which defines the temperature. That's why it is given the number 0. It came after first law of thermodynamics. This law came after first law of thermodynamics, but since it has so prime importance as it is defining something very basic to thermodynamics, the basic property temperature. So the temperature is getting a definition from Zeroth law of thermodynamics, this law of thermodynamics. So it must be given a number which must have higher importance than first law of thermodynamics. So it has been given the number 0, and it is called Zeroth law of thermodynamics. So today we'll see how we'll define temperature in terms of Zeroth law of thermodynamics. That will be the formal definition of temperature. Now just think and write your answer. Heat always flows from higher temperature to lower temperature. If I say heat always flows from the region of higher temperature to the region of lower temperature, is it true or false? Suppose we have a room, okay? And inside room, the temperature is 25 degrees Celsius, and outside the room, the temperature is 37 degrees Celsius. So what do you think, where the heat will flow? So I'm saying, will it be correct if I say heat will flow from the region of higher temperature, that is 37 degrees Celsius, to the region of lower temperature, that is 25 degrees Celsius? So heat always flows from higher temperature to lower temperature, true or false? Let's see. I think you must have got your answer. To check it out whether it's true or false, the answer is false. This is also a very conceptual point. The answer is false. Let's see an illustration. Suppose we all know the working of AC. Suppose you have an AC in your room. Okay, this is your room. And the room temperature is 25 degrees Celsius. And the outside temperature is 32 degrees Celsius. And say you have an AC in the room. Now what AC is doing? AC is taking the heat from the room, correct? AC is taking the heat from the room, and the outlet of the AC, this is the outlet of the AC, this is giving off the heat, and it is giving off the heat outside. So what you can see, what AC is doing is the AC flowing the heat from high temperature to low temperature or from low to high temperature. Clearly it is making the heat to flow from low to high temperature. So AC is making the heat to flow from low temperature to high temperature. So obviously this statement will be wrong. Heat always flows from higher temperature to lower temperature. This is one of the misconceptions which I see with many of the students. Okay, and same thing will be with the electric charge. Many think that positive charge always flow from high to low potential. No. So you can clearly see, first of all, that heat can flow from low to high temperature. That is for sure. Heat can flow from low to high temperature. But now point is that if we were at the word spontaneous, what is the meaning of spontaneous? Spontaneous means without any external aid, without any external agent, by itself. That is something spontaneous. Suppose you are releasing something. Suppose this is a pen. If I am just releasing the pen, it will go down. So matter spontaneously moves from higher height to lower height, correct? When we talk about matter, so matter spontaneously moves from higher height to lower height. That is the spontaneous phenomena. You need not to give any velocity for this. But if you want to throw the pen upward, it won't go spontaneously. You have to give some velocity. So this is a non-spontaneous phenomena. Okay. So first of all, be clear what is the meaning of spontaneous and what is the meaning of non-spontaneous. Spontaneous is something which will take place by itself, without any external agent, without any external cause, without any help. Okay. And non-spontaneous is something where you need to force something. You have to do some work. You have to take the help of external agent. Okay. So the correct statement is when two systems have a temperature difference, then the heat spontaneously flows from a system at higher temperature to the system at lower temperature. This is more precise statement regarding the flow of heat. Heat spontaneously flows from higher temperature to lower temperature. Got it? Heat spontaneously flows from higher temperature to lower temperature. We cannot say always. The keyword is spontaneously. So if there is a temperature difference and heat need to flow, if it has a choice, it will prefer to move from higher to lower temperature. For this flow, you need not to do any work. You need not to give any external agent, support or force to the heat. Heat will itself flow from higher to lower temperature. Got it? But it does not mean that heat cannot flow from region of lower temperature to the region of higher temperature. It can flow, but that flow will be non-spontaneous. That is, some work need to be done. Got it? This is very important point. In no way it is saying that heat can never flow from low temperature to high temperature. Heat can flow from low to high temperature as well, but that flow will be non-spontaneous. You have to do some work. Some external force has to be applied. Got it? So this is the correct. First of all, write this: spontaneous flow of heat. This is the correct concept. When two systems have a temperature difference, then heat spontaneously flows from a system at higher temperature to the system at lower temperature. And then write the note: it does not mean that heat cannot flow from region of lower temperature to the region of higher temperature. It can flow, but that flow will be non-spontaneous. That is, some work need to be done. Now, if you see this case, here the heat is going from low temperature to high temperature. Of course, we have seen it can flow from low temperature to high temperature, but the flow will be non-spontaneous. So you have to do some work, and the work is done by electricity. Here, the work is done by electricity. That's what AC is doing. You are supplying the electric energy to the AC, and that electric energy is doing the work and taking the heat from lower temperature to higher temperature. If you switch off the AC, the flow of heat will stop, because this is a non-spontaneous flow. If you switch off AC, this flow will stop. And will the heat keep flowing from outer 32 degrees Celsius region to inner 25 degrees Celsius region? Yes or no? Yes, it will keep on flowing, because this flow is spontaneous, high to low temperature. You need not to put any machine or electric energy for this. It need no external aid. This is the spontaneous direction of flow, high to low temperature, right? But this is non-spontaneous. So AC is doing what? AC is making the non-spontaneous flow of heat with the help of the electric energy. So is it clear now? Heat always flows from higher temperature to lower temperature. This is false. Actually, heat spontaneously flows from higher temperature to lower temperature. It can even flow from low to high temperature, but that will be a non-spontaneous process. We have to do some work in it. Okay. So let's see the meaning of temperature. The second meaning, one meaning we have seen in a very casual form, that is the degree of the hotness of the object. That's very lower class definition. Now let's elevate a bit. A scalar property of system which determines the direction of spontaneous flow of heat between the system and the surrounding. So you can say temperature is the property. You have seen It is the temperature which decides the spontaneous direction of flow of heat. Heat spontaneously flows from the region of higher temperature to the region of lower temperature, right? So which parameter is deciding where the heat will spontaneously flow? That parameter is the temperature. So in one way you can define temperature as a scalar property which determines the direction of spontaneous flow of heat between the system and the surroundings. Now let's see what is the meaning of thermal equilibrium. Suppose you have some object or system. Let us say a system, it can be a sample of gas, it can be any block, anything. Okay? And the system has certain properties. Okay, the system has certain properties. Say, pressure, volume, temperature, etc. Okay, so these are some of the properties of the system. And suppose there are two different systems, A and B, and you brought them in contact with each other. And from the surrounding, they are separated by adiabatic wall. From the surrounding, both the systems have been separated by adiabatic wall. Got it? So this is your adiabatic wall. What it means? It means now the two systems cannot transfer any matter or any heat with the surrounding, correct? No heat or matter can be transferred between the system and the surroundings. And between the system, suppose we have a diathermic wall. The system themselves are separated by diathermic wall. What it means? It means the system among themselves can transfer heat. Heat can be transferred between A and B, correct? Okay. Now say when you brought them in contact, and suppose at t is equal to 0, you brought them in contact in such a way that from the surrounding they are separated by adiabatic wall, and among themselves they have a diathermic wall. So it is observed that the properties of the two systems, like the pressure, the temperature, etc., will start changing. They will have fluctuation in their properties. The pressure will keep on changing, the temperature will keep on changing, and the rate of change is rapid at first and then keep on decreasing with time. Very important point. The rate at which the property is changing, the rate of change, is more initially, and that rate keep on decreasing. Okay, that means that properties are changing at a decreasing rate. Ultimately, the properties of the two systems become constant with time, and ultimately you will see all the property will become constant. I'm not saying same, I'm saying constant. It means if the pressure of A becomes say 5 Pascal and pressure of B becomes 7 Pascal, so now the pressure of A will not change further, it will remain 5 Pascal, and the pressure of B will not change further, it will remain 7 Pascal. Okay, so all the properties will ultimately becomes constant with time. This is the stage when we say the systems are in thermal equilibrium. Now, when the properties will become constant with time, you will say they are in thermal equilibrium with each other. Okay, this is the stage of thermal equilibrium. And in thermal equilibrium, one property must be the same for both the system. And this property is called the temperature. And when the thermal equilibrium will be attained, one property must be same for both the system. That property is called the temperature. So again, I'm explaining, see what will happen. Suppose ultimately the properties like pressure, temperature, etc. become constant. Say the pressure of A becomes 5 Pascal and pressure of B becomes 7 Pascal. Now it will remain at the value of 5 and 7. So you can see the pressure is not changing any further. That means the thermal equilibrium has been attained. Now you can surely say if the temperature of A is 100 Kelvin, so the temperature of B will also be 100 Kelvin. See, the pressure might be different, but the temperature must remain the same. That is the property of thermal equilibrium. So both will have the same temperature. Pressure may also be the same, but temperature must be the same. This is a very critical point. In thermal equilibrium, one property will become equal, that is the temperature. So two systems are said to be in thermal equilibrium if they have the same temperature with each other. Got it? Two systems are said to be in thermal equilibrium if they have the same temperature with each other. That is the meaning of your thermal equilibrium. Now let's see what is the zeroth law of thermodynamics. Very interesting law. It says if A is in system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, then A will be in thermal equilibrium with system C. Okay, so it simply says if A and B are in thermal equilibrium with each other, B and C are in thermal equilibrium with each other, then you can interpret that A and C will also be in thermal equilibrium with each other. Now, right now I said very interesting law. Now see one thing. Right now you have seen what is the meaning of thermal equilibrium. When two objects are in thermal equilibrium, they have the same temperature. Now the question arises, if two bodies are in thermal equilibrium, they have the same temperature. Now see the words which we have written. In thermal equilibrium, one property must be same for both the system. That property is called temperature. So temperature is defined on the basis of thermal equilibrium. Are you getting the point? Temperature is defined on the basis of thermal equilibrium and not the other way around. Thermal equilibrium is not defined on the basis of temperature. Are you getting the point? So if I say, which statement is correct? System A and B have same temperature and that is why they are in thermal equilibrium. Or B, system A and B are in thermal equilibrium and that is why they have the same temperature. This is a very conceptual point. Most of the students think there is no difference. They say if A and B are in thermal equilibrium, it means they have same temperature, or if they have same temperature, it means they are in thermal equilibrium, but both are not equivalent. So what do you think, which statement will be correct? System A and B have same temperature and that is why they are in thermal equilibrium, or system A and B are in thermal equilibrium and that is why they have same temperature? I guess you got it right. The correct statement is B. Okay. So your thermal equilibrium gives temperature the definition. Again, I'm repeating, get it very clearly. It is the thermal equilibrium which defines the temperature, not the other way around. So when two objects are in thermal equilibrium, then to have something same, some property must be same for both the system. That some property is called temperature. That some property is called temperature. Got it? So now, when we talk about first law of thermodynamics, zeroth law of thermodynamics, see. So zeroth law says, if system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, then A and C will be in thermal equilibrium with each other. Now, when we study zeroth law of thermodynamics, many of the students say, sir, it's obvious. What's the big deal about it? Like, see, Bob. Bob questions the existence of zeroth law of thermodynamics. He says, when two systems have same temperature, then they are in thermal equilibrium. So the logic of Bob is that, if two systems have the same temperature, they are in thermal equilibrium. So if A and B are in thermal equilibrium, B and C are in thermal equilibrium, then it's obvious that A and C have same temperature and they must be in thermal equilibrium. So what Bob is saying in the class, Bob has a doubt. He's saying I am a little bit of doubt for the existence of zeroth law of thermodynamics. Why at all we have this law? Because we know if two bodies are in thermal equilibrium, they will have the same temperature. So if A and B are in thermal equilibrium, they will have the same temperature. B and C are in thermal equilibrium, they will have the same temperature. So it's obvious A and C will also have the same temperature, so they must be in thermal equilibrium. So what's the deal about zeroth law of thermodynamics? Got it? What's the need for law about it? Can you explain? So see, basically, zeroth law deals with the thermal equilibrium. And thermal equilibrium defines the temperature. Temperature doesn't define the thermal equilibrium, correct? This I explained you in very detail right now. If A and B are in thermal equilibrium, then that is why they have the same temperature, not the other way around. So zeroth law is saying when you are talking about the zeroth law of thermodynamics, there is no role of temperature, because temperature itself is getting definition from Zeroth law and thermal equilibrium concept. So you cannot apply this logic here. This could have been the logic had the concept of thermal equilibrium been derived from the concept of temperature. But here the things are going in the opposite way. The thermal equilibrium is defining the temperature. So you cannot define something on the basis of something which itself is derived from that law. So temperature comes secondary, primary is the thermal equilibrium. So that is the significance of the Zeroth law of thermodynamics. We don't know anything about temperature when we are talking about thermal equilibrium. So when A and B are in thermal equilibrium, B and C are in thermal equilibrium, then Zeroth law say A and C are in thermal equilibrium. Yes, you can explain this law now. You can convince yourself this law with the definition of temperature by thermal equilibrium. You say yes, Zeroth law is in agreement with the definition of temperature which has been given by thermal equilibrium, because when two objects are in thermal equilibrium, they have some property as same, which is called temperature. So when A and B are in thermal equilibrium, they must have same temperature. B and C are in thermal equilibrium, they must have same temperature, and so will be the case for A and C. So this is your Zeroth law of thermodynamics. This we have done. Now let's see. Heat is a form of energy. Heat is a form of energy. So the unit, and heat we usually denote by capital Q in thermodynamics. And we will give some algebraic sign convention when heat is transferred to the system throughout the course of thermodynamics and kinetic theory of gases. When heat is transferred to the system, that is, heat is absorbed by the system, we will give Q algebraic sign positive. And when heat is transferred out of the system, that is, when heat is given off by the system, we will take Q to be negative. Okay? To illustrate, a system absorbs 30 joule of heat. So it is absorbing. So Q will be taken as plus 30. A gas gives off 25 joule of heat. Gas is giving off heat. So Q will be taken as minus 25 joule. 40 joule of heat is given to the system. So heat is given to the system, Q is 40 joule. Got it? So this will be the algebraic sign of Q. When heat is given to the system, take Q positive. Heat is given out of the system, take Q negative. In our model of thermodynamics and kinetic theory of gases, whenever we will denote Q, we will denote it heat given to the system or heat gained by the system. We will never talk about heat given off by the system or heat lost. We will always talk heat gained, and we will write Q. Now, if our Q comes to be positive, heat is actually gained, because we have taken the convention for heat gained. Okay? And if your Q comes to be negative, what it will imply? Heat is actually lost. So suppose you're doing some numerical problem and you got the answer as Q is equal to 25 joule. So what you can write? Heat gained as 25 joule. This is the answer. And if suppose you want to write heat loss, so you can write negative of this, minus 25 joule. This represent both of these things. If your answer came to be, say, you're doing some numerical and your answer comes to be minus 30 joule, Q comes to be minus 30 joule, and your Q represent heat gained. So actually heat is lost. So what is the heat lost? 30 joule. And if you want to say in the notation of heat gained, so you can write minus 30 joule. Okay? So throughout the thermodynamics and kinetic theory of gases, in our model, Q will represent the heat gained. It can be positive or it can be negative. Got it? Now let's see the different scales of temperature. So measuring the temperature, we need some scale, some unit. There are many scales like Celsius scale, earlier called centigrade scale. Centigrade means in Latin 100. Later the scientist came Celsius, whose name has been replaced with the centigrade. Fahrenheit scale, Kelvin scale, Rankine scale, Newton scale. The more 3 and 4 scales. But we will focus on 3 scales, which will be the scope of your present syllabus: the Celsius scale, the Fahrenheit scale, and the Kelvin scale. Got it? And we will see how the scale is formed and how the conversion of temperature value can take place from one scale to another scale. And you can convert to any new hypothetical scale too once you learn the method. See, in any temperature scale, there are two fixed reference points. Remember, in any temperature scale, there are two fixed reference points. We take two values as the fixed reference point and give some values of temperature, in that particular scale to these two reference points. The two fixed reference points are the ice point of water. You can also say the freezing point. Never say 0 degrees Celsius. No, that Celsius will come in that particular scale. Right now we are just talking about the point, ice point of water, and the steam point of water, which is called the boiling point. Okay. So these are the two reference points that will be taken in the scale, and they will be given some reference temperature values. We will see. And let delta T be the difference between the 2 points, range of the temperature. Delta T be the difference between these 2 points. Suppose this is 100 and this is 30. So the difference will be 100 minus 30, that will make it 70. So it is a difference. Now, if you take this thing, difference of the two temperature divided by the range on that scale, the difference divided by range. So for each scale, this ratio is constant. That is the fundamental for conversion. This principle is the fundamental for conversion. For each scale, this ratio, the difference of the temperature divided by the range, is constant. Okay, let's see. First of all, let's see the notation, how we write the temperature. When you're writing any particular temperature, then we first write the degree and then the unit, like degree Celsius, degree Fahrenheit. When we write the difference in temperature, then we write first the unit, then degree, Celsius degree or Fahrenheit degree. Like when you write boiling point of water, so we write 100 degrees Celsius. And if you write difference between freezing and boiling point, then we write 100 Celsius degree. So this is very precise thing. However, most of casual books or casual examinations doesn't follow this very strict rule, and they simply write, usually you will find in many books both are written like first degree and then unit. Okay, but precisely this is the rule. When you write the temperature, first we write the degree, then unit, and difference in the temperature, first unit, then degree. Okay, but you will find in your syllabus or most of the books, you will find the same notation for both things, degree, then unit. Now, if you see the steam point, this is your steam point, ice point, and range. So for Celsius scale, 100 degrees Celsius is taken as the reference of the steam point. 0 degree as the ice point. So the range will be what? 100 minus 0, 100, correct? In Fahrenheit, the steam point is taken as 212 degree Fahrenheit, ice point as 32 degree Fahrenheit, and range is 180. In the Kelvin scale, in Kelvin there is no notation for degree. We simply write K, capital K. The steam point is 373.15, which usually we take as 373, round off. The ice point is 273.15. We take as approximated, round off 273. So the range is 100. Okay. So these are the steam point, ice point, and range for the three famous scales. You can note it down. Now see, when you convert right now I told you for any scale, this value, the higher value minus the lower value divided by the range is constant. Correct? Suppose you have to convert Fahrenheit and Celsius and vice versa. You have to convert Fahrenheit into Celsius or Celsius into Fahrenheit. So suppose the temperature in Fahrenheit is TF and the temperature in Celsius is TC. Okay, what is this I'm taking as the higher temperature. What is the lower temperature? So let's see the lower range. The lower range, the ice point in Celsius is 0 and Fahrenheit is 32. So this is 32, lower range of Fahrenheit. This is 0. What is the range? Delta T. So in Fahrenheit, what is the range? 180. In Celsius, it is 100. 180 and it is 100. Okay. Now you can apply this formula. T higher of Fahrenheit, TF, minus T lower, 32, divided by range, 180, is T higher of Celsius, TC, minus 0, divided by 100. Now say this will be 5, this will be 9. So you'll get TF minus 32 is what? 9 by 5 TC. Correct? So you got the formula for conversion. So therefore, you will get TF, temperature in Fahrenheit, is equal to 9 by 5 of temperature in Celsius plus 32. So you derived one formula which will give you the temperature in Fahrenheit if you're putting the input as temperature in Celsius. And simply pay care for the base rule. As I told you, I can also give you, when you will do the DPP, you'll also find some new hypothetical scales. Like suppose if I say there is some new scale, a Joule scale, where the reference point, ice point, and the steam point are this and this is the temperature in Fahrenheit converted into the new Joule scale. So you need not cram the formula. You will apply this concept. Higher minus lower divided by range is constant. From this, you can also change simply the simple mathematical skill. If you need to get TC, so you can 9 by 5 TC will be what? TF minus 32. So TC will be 5 by 9 TF minus 32, correct? So if you have a temperature in Fahrenheit, you can convert into temperature in Celsius. Straightforward, nothing new. If you remember this thing, you can easily, if you need not to remember these end formula, you can easily convert. Okay, higher minus lower divided by range is same as higher minus lower divided by range. Got it? Okay. Now, if you want to convert from Celsius to Kelvin, so say in the higher range, higher value, you're taking TC, and Kelvin it is TK. Lower it is 0, and here it is 273. Correct? It's exactly 273.15, but round off we take 273. What is the range? So here range is 100, and in Kelvin also we have a range of 100. Can you see? So we'll get higher TC minus lower divided by range is equal to higher minus lower divided by range. 100 will get cancelled away, and you'll get temperature in Kelvin as temperature in Celsius plus 273. See, this is the value you got. Okay. So this is the conversion between Kelvin and Celsius. Celsius plus 273. Now let's see the unit of heat energy. Since we have seen heat is a form of energy, so it will have the same units as the energy or work. So the SI unit of heat is joule. The common unit is calorie, CAL, small CAL, and 1 calorie is equal to 4.18 joule. This is the conversion factor. The nutritional unit, when you eat something, you say it has so much calorie value. This calorie is different from this calorie. This is written as capital CAL. This is the nutritional unit. This will have very little use in this subject. This has a nutritional value, capital CL, and it is basically 1 kilocalorie. If you talk about this calorie, capital CL, this is 1 kilocalorie, 1000 small CL. That is the common unit of energy. Okay, we'll mainly focus on these two units. Now let's see what is the mechanical equivalent of heat. Now see, we know heat is a form of energy and work is also an energy in transit, so both can be interconverted. So Joule found that by doing the mechanical work, you can convert the work into heat. Okay, so when you are converting work into heat, so the ratio of the work and heat is a constant, provided there is no loss of energy in other form. This ratio is constant, and this ratio is called mechanical equivalent of heat. Mechanical equivalent of heat, and this comes to be 4.18 joule per calorie. It means 1 calorie of heat is equivalent to 4.18 joule of work. That is the meaning of mechanical equivalent of heat. This is the mechanical equivalent of heat. 1 calorie of heat is equivalent to a mechanical work of 4.18 joule. Okay, this is the mechanical equivalent of heat. So that's the end of your lecture 1. And lecture 1 is the introductory lecture, making your concepts in heat, temperature, temperature scales, Zeroth law, thermodynamics, definition of temperature, thermal equilibrium. Okay, these are the very basis of thermodynamics. In second lecture, we will start with, that is the code TPA02. What is the meaning of specific heat capacity? And then we'll see in lower classes too, you did with the problems of specific heat capacity. But now we will also see the case of variable specific heat capacity, where very beautiful problems are formed, both in mathematical form, calculus, as well as graphical. How the specific heat capacity varies with temperature, and the integral and graphical approach for solving the problems. Then we will see the concept of heat capacity, and same thing, the numerical problems. Then we will see what is the meaning of water equivalent of heat, and then we will see the calorimetric problems, like when how much heat is transferred when you're heating something, when you're dropping a coin in the beaker, what will be the final state, when you're mixing the ice with water, then after how much time, what amount of ice will be left, all such kind of things will come in these kind of problems. But before proceeding to lecture 2, you must have, number 1, make the notes of lecture 1. Number 2, enter in any doubt or discussion in the panel or get in contact with me. Number 3, complete the workbook, the work assignment of lecture 1 TPA01. And number 4, give the minor test of TPA01 to have full perfect command over the concepts of TPA01